In this video, I am going to explain the concept of Joule Thomson effect and how it can be exploited in a refrigeration effect. So basically we have a cylinder and a piston over here, and we have a narrow section and another piston and a cylinder over here, and basically we have a gas inside this piston, inside the cylinder, and we constantly apply a pressure P1 to it, and the initial volume is V1, and we allow this gas to expand into the narrow section, and in this cylinder 2 we have a piston and we constantly apply a pressure of P2 over here, and let us assume that the pressure 1 is greater than pressure 2. So that means we are giving a greater pressure to piston 1. So eventually what will happen is that this gas, due to the high pressure of P1, will try to force through its narrow pipe and will get expanded to a final volume of V2 over here. So initially the gas in this cylinder was at a volume V1, and finally it has reached to a volume 0, and the full gas over here has expanded into this piston. So initially in this cylinder the volume of the gas was 0, and in the final stage the volume of V2. So we are going to apply the first law here. First law. This dq is going to equal to du plus dw. So we are going to assume an important case here where this entire setup is insulated, so there is no heat transfer, so this whole setup is adiabatic. So this automatically means rate of heat transfer is 0, so dq is going to be 0. So applying this we will get 0 is equal to du plus dw. So this means minus du is equal to dw. So minus du is nothing but minus of u2, change in internal energy, is equal to the work done. So u1 minus u2 is nothing but dw. Now let us carefully observe the work done. Work done is nothing but P into integration of P into dV, which is nothing but P into final volume minus initial volume. So for this cylinder 1, the work done is nothing but P1 into the final volume is 0 here. So 0, and initial volume is V1, 0 minus V1. And for this cylinder the pressure is P2, so P into dV, P2 into dV. So final volume is V2, so V2, initial volume is 0. So this gives us U1 minus U2 is equal to minus P1 V1 plus P2 V2. So rearranging this term, we will get U1 plus P1 V1 is equal to U2 plus P2 V2. Now carefully observe this term. This term we have already studied that a term H enthalpy is equal to U plus PV. So this automatically gives us H1 is equal to H2. Or in other words, enthalpy is going to remain constant. So this process, Joule Thomson effect, it is defined by a process called throttling process, where a gas is forced to expand to a narrow section, and this process is known as throttling effect. So throttling is nothing but is an isenthalpic process. I mean, enthalpy is going to remain constant. So when you are expanding the gas from pressure 1 to pressure P2, obviously there will be a drop in temperature. So this gives us cooling effect. So in this Joule Thomson effect, the important term here is If we are expanding, say we are expanding a gas from 3 bar to 1 bar, so obviously there is a change in pressure dP. So if we change the pressure, what will be the change in temperature, del T? So this term is very important over here. So this Joule Thomson coefficient is defined as the change in temperature with respect to pressure. So this entire process happens at constant enthalpy. So this is nothing but our Joule Thomson coefficient. So by expanding, we are getting a drop in temperature which further produces a cooling effect. So this is nothing but a Joule Thomson effect or throttling process. So let us see some cases where the Joule Thomson coefficient for an ideal gas or a real gas. For an ideal gas, we knew that we already derived that enthalpy is constant, or in other words, H1 is equal to H2. So for an ideal gas, enthalpy is just a function of temperature. So Cp into T1 is equal to Cp into T2, or T1 is equal to T2. So there is no change in temperature for an ideal gas. So this term over here, dou T by dou P, is going to be 0. So for an ideal gas, Joule Thomson coefficient is 0. So the physical meaning of this 0 Joule Thomson coefficient, no matter how you expand the ideal gas, no matter even if you decrease the pressure from 3 bar to 1 bar or 2 bar to 1.5 bar, if you allow an ideal gas to expand, there will be no drop in temperature and no cooling effect. But for a real gas, we knew that H1 is equal to H2. For a real gas, enthalpy is not just a function of temperature. So T1 is not going to be equal to T2. So there will be some drop in temperature, or T2 is going to be less than T1. So there is going to be change in del T. So the Joule Thomson coefficient will be greater than 1 for a real gas. And this effect is exploited in many industrial applications to produce cooling effect.